Right, we are working on chapter 6.4, which is work. Right now, this one, and I know how many, I'll see how many I do, but at least one more, if not two more. We're going to do lifting things out of holes in the ground. So we're going to look at how do you calculate the work done in lifting something out of a hole or lifting something from the side of the building, which is kind of where we left off last time. And then after that, I will do some chains. So we're going to list some chains, which is kind of similar to that. And I don't know if we'll do the water ones. I'll see how much time we've got, because they do take a lot of time. Okay, here's a version of question 10. What you've got is a mine shaft, which is what that's meant to be. In my question, it's 400 feet. There's a rope, and at the end of the rope, there's 750 pounds of coal. And we're going to move that from the bottom to the top. And we're being asked to calculate how much work is done in moving 750 pounds of coal with this particular weight of rope from the bottom of the shaft to the top. And essentially, these questions involve us finding the force function. And the force function is position x, right? F of x, is the weight of everything at some position, we'll call it x. Now, I'm going to call x the distance from the top to here. If I measure x in that direction, it just makes the calculation a little bit easier. So our force function is going to be the weight of the rope at position x. Now, you're told that the rope in this story, is more like a chain at that way, is 8 pounds a foot. And x is that distance. So if x was 3 feet, it would be 8 times 3. If x was 20 feet, it'd be x times 20. Since there's x feet of rope, the rope is going to weigh 8x. Are you comfortable about that 8x and how I came about it? Right. Now, in this story, don't we also have a lump of coal stuck to the end of the chain? And that lump of coal weighs 750. So won't that also contribute to the weight? So at position x, wouldn't the total weight of everything be a rope plus a lump of coal? And that's our force function. So you want to find the work done. It's going to be the integral from a to b of the force function, dx. And that's going to be the integral from 0 to 400. And it's going to be 8x plus 750 dx. Are you comfortable with where I'm getting this 0 to 400 from? Do you understand where in the story that comes in? Would you agree that's a very nice integral, just ugly big numbers? So I'm going to go dot, 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 and do not be surprised if you get 125,000 foot-pounds. Do not be surprised by how big these answers are, right? Because sometimes they freak you out and you think you're wrong because they're just too big. You could even get millions in some stories. So far, so good? Our first one?
The answer is 940,000 foot-pounds.
Wow, for this one. 940,000 foot-pounds. Okay. Do I need to do another one of these ropes with something attached to the end? Or can we call that one good? Your choice. You want to see another one with just different numbers just to get a feel for it? Or are you good with this one?
What is it looking for with the first part of question 10 with the limit?
Oh, thank you. I forgot all about that. The way that I do these questions, there is nothing in this that has a Riemann sum in it. But WebAssign, being WebAssign, wants us to write down what the Riemann sum for this would be. So let me just show you what it is. You're going to find the limit as n tends to infinity, but that'll be in the question. You're also going to get sigma. Is it K? I guess I should find out what letter they're using.
I equals
I.
1.
Okay, so it's going to be I equals 1 to N. And in here, you put the force function. Only you call it xi. And the x. You remember doing Riemann sums? I know we didn't do a lot of them, but doesn't this thing turn into the integral? So all you'll do to keep WebAssign happy is this piece here, which is force function, you fill it into here with a delta x at the end. And that will keep them happy. I do not solve these questions by using Riemann sums. Are you not glad that I don't solve these questions with Riemann sums? It's just in my brain, it's much cleaner to just find the force function and integrate it. But I mean, this is a valid way of solving it. In fact, after they do that, the next line is they write this down anyway and they get the same answer. So it's not like they're going to do different calculations. I think this is just the theory. If you want to know where does this damn thing come from, they imagine that you've got a position, but it won't be called x, it'll be called xi. And they move it just a tiny bit, and the tiny bit they move it is delta x. And this calculation would be the work done in just moving it a tiny little piece. And then you add up all the pieces by making each piece infinitely small. So it's a thing, I guess it's the theory behind why this works. But I quite like the fact that it works, and I don't dwell on the theory of why it works quite as much. Does that help? So you're going to get this guy, and you're just going to fit him in here with a little delta x to keep WebAssign happy when they ask for it. I don't think they ask for it all the time, but when they do, I'll do that one there. And do that one there. Right, so I was saying, are we okay with the rope question, or do you want to see another rope with something attached before I move on to the next kind of pulling things out of holes in the ground? Nobody's willing to share that. Okay. Then you're going to get number 13 now. Question 13 is quite convoluted, so let me show you what it looks like, and then I'll move on and start solving it for you. Right, here it is here. A leaky 10 kilogram bucket. So this one has metric, right? Kilograms. And one of the things you have to watch out for when you see kilograms, will you please remember to use 9.8? Remember that funny gravitational constant that pops in when you do kilograms. Now it's a 10 kilogram bucket. It's lifted from the ground to a height of 13 meters at a constant speed. And the rope weighs 0.7 kilograms a meter. Now the funny part. Initially, the bucket contains 39 kilograms of water, but the water is going to leak out at a constant rate and finishes draining just as the bucket reaches the top, the 13 meters level. How much work is done in doing that? And they remind you about the 9.8. So we have got a lot of stuff happening in this story, agreed? There's pulling a bucket of water up 10 meters and then finding out. I'm trying to get my, okay, where are you hiding? Okay, I'm having window issues, guys. Bear with me while I figure out where the heck our guy has gone. Is he hiding? Oh, he's hiding over here. I've got two screens. Would you believe it? The windows keep jumping for some strange reason. Okay, focus. If you could keep track of all that information, I've got it beside me, so I guess I can do it. What we have, right, I like drawing pictures. It helps me visually. So we have got story that looks like this. This is the ground. And we'll have this as a building just. And it's 13 meters, right? So from there to there, that's 13 meters. That's cool. And we are going to have a bucket that weighs 10 kilograms. It's got 39 kilograms of water in it. Okay, that's going to be interesting. So here's my little guy. And here is a snapshot of this story. And the information that we're given is the density of the rope. And the rope weighs 0.7 kilograms per meter. Okay. We have a bucket. And the bucket is weighs 10 kilograms. And then we have water. And the water starts at 39 kilograms. It's leaking. So I'm going to do my usual. Imagine a little snapshot of X. We are going to create f of X, which is the weight of everything. At position X. If you take into account the weight of everything at this position, and would you agree it's made up of a rope, a bucket, and water? So it's going to be WT short for weight. It's going to be the weight of the rope plus the weight of the water plus the weight of the bucket. And this is going to be at position X. Okay, the rope's pretty standard. That distance to X is here to here. If that's X meters and the rope weighs 0.7 kilograms per meter, the weight of the rope is going to be 0.7 X. Are we comfortable with that? Right. Now, the weight of the bucket's the easy one. Isn't the bucket going to weigh 10 kilograms all the time? Right, it doesn't change. It's 10 at the beginning, it's 10 at the end. Now the tricky one. What is the weight of the water? Now the weight of this water is a bit strange. At the bottom, it weighs 39 kilos. And as it gets raised upwards, it leaks. And it leaks in a very strange way. By the time it reaches the top, it's empty. So at any given point, won't the weight of the water keep changing? And won't the weight of the water depend on the position that it's in? Now I'm going to make an assumption here which kind of turns it on its head. I'm going to look at how much water is left rather than how much water is lost. If it's 39 kilograms and it's 13 meters, would you agree that it loses 3 kilograms of water for every meter it travels, right? But at position X, won't there be X meters of water left? And if 3 kilograms per meter, won't there be 3x kilograms of water left? So I'm making that guy 3x. Now, if you don't like the way that 3x came from, let's look at it from a different perspective and get the same answer. Okay. If this is X and the total thing is 13 meters, then won't this distance here be 13 take away X? Agreed? Now, if you want to know how much water has been lost, won't it be 3 times 13 minus x? Right, for every meter, it loses 3, right? So if that's 13 minus x, won't you lose 3 times that? Now that's 39, take away 3x. Now, if that's how much you've lost, how much is left? 39, take away what you've lost. 39, take away this guy. And guess what? Can you see you still get the 3x? So it depends on how your brain sees it. The way I see it is I just figure out how much water is left right away, right? Which is 3x. For every meter, you're going to have 3. Well, the work done then is the integral from a to b of the force function dx. In this case, 13 meters is 0 to 13. And the force function, well, combine them, you get 3.7x plus 10, and you'd have a dx. But actually, I've kind of missed out something. What have I not taken account of yet?
Gravity.
Yeah, so you stick a 9.8 there. And if you want to make your life easy, I don't know how easy it is, won't it probably be less work to just stick it outside the integral and multiply it at the end? And so you do your usual calculation from that point. Do you see how convoluted this particular version of pulling something out of a hole in the ground is? But that's as bad as they can get. Do you want to see another one where a bucket of water or coal or whatever is getting pulled out of a hole in the ground? Do you want to see another one like this?
If you could, that would be nice.
Okay, so let's
For that one, the answer is 4,337 foot-pounds.
say that number again.
4,337.9 joules.
Okay, there you go. Yeah, let's do another one. Won't change my picture much. No one's commented on how good my drawings are. I mean, is that not a pretty cool stick figure? Yeah. Okay, we'll keep it in the. Do you want the next one to be foot-pounds, or do you want me to do metric? The only difference between the two is one of them you multiply by 9.8 and the other you don't. So do you want this story to be in feet and pounds, or you want it kilograms and meters?
Can we do kilograms and meters?
Sure. So let's have a coal mine story then. So this coal mine is 200 meters deep, which is nothing. And the rope weighs 5 kilograms per meter. And the bucket in this story weighs 80 kilograms. And the coal inside it weighs 100 kilograms, but you're losing it. And you're losing it in such a way that by the time the bucket gets to the end, it's empty. It's always going to be, by the time the bucket gets to the end, it's empty. So it starts off with 100 kilograms, but as you pull it up, lumps of coal keep falling out a hole in the bottom or whatever. And when you get it to the top, the bucket is empty. Whenever I remember being at school and getting these stories, and I always thought to myself, why didn't they just plug the bloody hole up at the bottom and make this question so much easier. Because wouldn't it be a lot simpler mathematically? But evidently, because it's an engineer, he didn't think of that. So let's find out from this story the force function. So it's going to be the weight of everything. At position X. And in my story, we're measuring it from the top. So there's X. Well, I know this one is made up of the weight of the rope plus the weight of coal plus the weight of the bucket. Right, when you've got X meters from the top, X meters of rope at 5 kilograms a meter, 5X. Weight of the coal, we'll leave that for a minute. The weight of the bucket is a fixed amount, it's 80. The weight of the coal, well, I have to do a little calculation here. 100 kilograms of coal leaking out over a 200 meter space means the rate at which you lose the coal is going to be 0.5 kilogram per meter. You comfortable about how I figured out the rate at which you were losing coal in steady water in this case? Does anybody want to tell me what the weight of coal would be? What would be left when you're X meters off the top?
I got 1/2 X.
Agreed. Now you can count it the way I do. I just count it how much is left. But couldn't you figure out how much you lose and then take it away from 100? And guess what? You would still get the same answer, right? So it's not like you'd get a different value, which means in this case, 5.5x plus 80. So the work done is the integral of the force function from A to B. And this will be from 0 to 200. And we can do, I'll stick the 9.8 outside again. And that way we can just do this guy. And then at this point, you can just do the integral and off you go. Have you noticed that once you've got a template to these, don't they just change the numbers? They don't really change much else. I'm not. So, you know, I could do another one where the rope weighed 10 kilograms a meter, that there was 3,000 kilograms of water, and it was a 200-meter hill, and you lost all the water by the time you reached the top, and the bucket was 82 kilograms or whatever else. But all that would really be changing are the numbers that go here. It would look virtually mathematically, it would look virtually the same question. Are we good on this? Okay.
What would it look like if over the 200 meters you only lost 50 kilograms of coal?
Oh, then you would have 50 plus 0.5 x.
Okay.
So you figure out what's left, and that's a fixed amount, right? Because that's always going to be there. And then you look at what extra is there. And it depends on the rate it's losing. I guess I might have to change that because you won't be losing 100 over 200. Wouldn't you only be losing
like
50?
1/4.
So it'd be a quarter. That's how you would tweak it. I haven't seen one like that, but that would have probably been a better question, actually.
For the answer to the question as written, it's 1, 2, 3, 4, 800.
Oh, would you look at that for symmetry? Now, if I really played it, couldn't I have got 5, 6, 7? But that was just a random question. Okay, we are moving on. We are now going to look at chains. How hard could a puzzle with chains be? quite hard is the answer. Here is the ground. And here is chain. Oh, and I better pick your question. I think it's question 11. Yes. So this is going to be a version of question 11. So we have a chain on the ground. And this chain is 10 meters long. And what do we know about this chain? The mass of the chain, which is its total weight, is going to be 80 kilograms. And we are going to take one end of this chain and we are going to pull it off the ground. Now, we could just pull the whole chain up, but they're not going to make your life quite as easy as that. When it's finished, it's going to be 6 meters off the ground. So it's going to look something like that. And that distance there is going to be 6 meters when it's finished. So it's going to go from here, that's like the before, and here is like the end. And we're going to calculate what the work done in moving this chain, right? Basically picking it up, right, and pulling it off the ground. And let's do the construction of it. I'm going to imagine that this distance from here to here is X. So basically a little snapshot, right? It's not the start, it's not the finish, it's kind of somewhere in the middle. What would the situation look like? It would look like that. And we know what our force function is. Our force function is the weight of everything at position X. Now, back to this guy. 80 kilograms, 10 meters of rope. Then doesn't that mean that the rope weighs density 8 kilograms per meter? And you need that number. Are you happy how I calculated it? 10 meters of rope weighs 80 kilograms. So the density of that rope is 8 kilograms a meter. Are we good? Right. Now, when you are pulling this chain up, do you know the only weight that you're actually pulling against is the X meters? The stuff that's on the ground isn't a problem. It weighs nothing, right? All you're holding on to is the end of a chain, and it's X meters off the ground. So won't the weight of that chain simply be AX? Does that make sense? That's the bit that you're holding on to, right? That's the weight. Couldn't you cut the chain there and it would still weigh the same, right? All you're holding on to is X meters of rope that happen to weigh 8 kilograms a meter. So that's your guy. So the force function was actually quite simple. And so the work done is going to be the integral from 0 to 6 meters, because the story was you only pulled 6 meters off the ground, right? You didn't pull the whole 10. So if it was 6 meters, 0 to 6 of 8x dx. And who have I forgotten?
Gravity.
So if I stick in 9.8 at the end, can we call that good? And we've done our first rope or chain pulling question.
1411.2.
I want to put that 0 in. There we go.
Really wanted to be there.
It probably did. Now, there's another chain question, which I'm trying to find now because it's to do with a chain that's hanging from the ceiling.
12.
12, okay. So what you got here is a chain dangling from the ceiling. And it's a 10-foot chain. So from here to here, it's 10 feet. And we know that this chain weighs 45 pounds. So if we're talking about the chain, it weighs 45 pounds. There's 10 feet of it. So the number we're interested in is the density, which is 4.5 feet per pound, right? And in this story, you're going to pick this chain up and you're going to pull it until it hits the roof. So when you're finished, it will look like that. Maybe not to scale, but when it looks like that, would you agree that basically it's 5 feet both sides? So far, so good. You kind of visualizing the story. I like pictures. You might not need these pictures, but for me, they help. So now I'm going to do a snapshot. And I am going to call the distance from here to here X. So I now need to find the force function, right? Now the force function is going to be the weight of everything at position X. So here we have a little bit of a hiccup. I'm about to write the wrong answer deliberately. Now I want you to figure out what the right answer should be. Oh, I got this. If you imagine that's my hand holding the thing, I've pulled it up this X meters and it's 4.5 a pound. So the weight function, right, the force function is 4.5x. Now, if that's your hand holding this chain, whatever you want to call it, rope, that is not the total weight. What is the total weight? Okay, how much chain are you holding on to?
You're holding on to the full 10 feet.
But how much is going to be pushing against you? How much of that 10 feet are you holding on to? Are you pushing
Only,
against?
only the X portion, right? Only the growing part of the chain is going back up.
What about this side? Aren't you also holding that up off the ground? The bit above is being supported by the ceiling, but anything from the top of your hand downwards, no matter where it is something that you're holding on against. What does that make it? It means that this fella is 4.5 times 2x. It makes him 9x. Now, I hope some of you engineers and physics people, that makes sense to you. Maybe for some of the mathematicians, you're not saying this, but if you were holding on to something there, aren't you holding on to this piece of rope? But aren't you also holding the weight of this other piece at the other side, right? X and X, 2x. And so your work done is the integral of the force function. Since this is feet and pounds, I don't need to correct it. What are the two numbers that go in my integral?
5 and 0.
Okay. Why isn't it 0 to 10? Why is it 0 to 5? I mean, there's 10 feet of rope, but it's only 0 to 5.
You have it bent over itself. 0 to
just-
10 would be if you like pushed it through the ceiling, right?
Yeah, if you took the entire rope and taped it to the ceiling or something, right? Then you'd be using this. But you know, in the story, you did it until the bottom, you know, the piece at the bottom reached the ceiling, and you end up with a big U shape of rope. And that is our second kind of, I'm not sure what I'm calling it, chain story, rope story. Do you want to see another one?
Please.
Okay, so let's make up one. Let's have another piece of rope. Let's have this rope weigh, not weigh. Let's make this distance 20 feet. And this chain or rope, I'll call it a rope this time, weighs 50 pounds. But that becomes 2.5 pounds per foot. Now, do you want me to do a story where I pull this back up onto the ceiling? Or do you want to do a story where I pull this right up so that it's going essentially through the roof? Which version? Do you want another one that looks like this? So you get the rope and you pull it until it's at the top, so it makes a kind of U shape. Or do you want me to pick it up and pull it totally flush with the ceiling, essentially? Which one do you want? I don't care.
We do another U.
We'll do another U. So we're going to pick it up until it reaches that shape. Now, when that happens, are we all comfortable that it would be a 10-foot worth of chain being pulled from the bottom to the top? Now what we do is we create my kind of snapshot. So we're about here. And I'm going to call this distance X again. And so our force function is basically going to be the weight of everything, which in this case is just how much chain am I actually supporting? And the answer is I'm supporting these two pieces. In other words, the length of the rope I'm supporting is 2x, right? One on each side, multiplied by the density. In this case, the force function is now 5x. And so the work done is going to be the integral from a to b of a force function. In this story, from 0, which would basically be this position, to the end, which would be this position. So from 0 supported to we got 10 feet of a 5x dx, and you'd finish at that point. Are you good? Any questions with that? If I was going to do the other story where this actually ended up looking like this, I can't draw it much, but can you imagine you pulled it so it was all on the ceiling? Wouldn't this become 0 to 20? And wouldn't that still be 5x? Now, aren't you glad there's not a bucket with coal that's leaking at the end of this thing? Well, I'm glad there isn't.
So
is it?
far, at least.
Yeah, there isn't going to be one. I guess I keep forgetting. if the question has one of these fellas, that bit's always given to you, right? So, and actually, so's that bit given to you. So if you have to fill in one of these, well, you just take that 5 guy and just call him 5xi and keep WebAssign happy. Right. So whatever your f of x is, just put it in here. And that'll do that bit. I'm just looking at one of the questions that involved them and they had that. Well, I guess I thought we might get to this point. We still have one more work question to work through. I deliberately thought that one. It wasn't an accident. You get it? One more work question to work through. Whew. God, that was a good joke as well. So what have we missed? What have we do? We'll do it tomorrow. We are going to figure out how much work is done in pumping water out of pools. So you're going to get a swimming pool or a oil tank, cylinder,